All right, we're here. Good morning. Hope everybody's having a good day. We did not get a snow day today. Someone asked in chat, will we have time for questions or should I wait till the end of class? We always have time for questions. Please do not wait until the end of class. If you got questions, just go ahead and ask them, even if I forget to say any questions. So, yeah, go for it. What do you got? Okay, I'm not hearing any audio, but I see your microphone moving. Okay, hold on a second. Let me try this. Thank you, Zoom. All right. Sorry, go ahead. Try your question again. It should work this time.
I had a question
There we go.
about combining the addition operations, I guess, because I did the binary numbers and then the choose representation of the negative number.
Mm-hmm.
Combining them doesn't really make sense because just 1 plus 1 equals 0, I guess. I think I'm combining it wrong because I got the wrong answer than I was supposed to.
So you did 1 plus 1 and got 0, you said?
Well, actually, that's what my logic was, but I'm not really sure how I got here. Yeah?
All right. So
Combining part doesn't make sense.
So let's start with 1 plus 1. That's a good one, right? So this is 1. This is 1. Do your pencil and paper addition column by column. 1 plus 1 is 0 with a carry. 1, 0, 0 is 1 with no carry. All of these come out to 0. And that's the binary equivalent of 2.
Okay, so you carry. Gotcha, alright.
Okay.
So, right.
Now if we try...
The carry part and, alright, I see now.
Okay. And one of the keys is you got to make really sure that you're using the right number of bits. So if we're doing 8-bit addition, right, go ahead and put in those 7 zeros in the front. Especially when you have negative numbers, those will make a big difference.
Alright, I see.
And then...
I see how I got it wrong.
Okay, cool. The other thing to keep in mind with just with 2's complement, if we do, say, 8-bit 2's complement, it turns out this bit over here is the sign bit. 1 equals negative, 2 or 0 means bigger than or equal to 0. So if you convert a number, if you express a number in 2's complement, this most significant bit tells you whether the number is negative or not. That's just kind of the way it works out.
Alright, thank you very much.
Alright, you're welcome. So while we're on the subject of 2's complement and negatives, let me mention something else, which is signed magnitude. And remember, when we choose to use binary to represent information, we can kind of do whatever we want, right? If there's no laws about this, we could represent numbers in whatever way we choose. And for us, we're always going to do, pretty much always going to do weighted positional notation. And if we want to include negative numbers, we're going to use 2's complement. But there's other ways that we can write integers, and one such way is something called signed magnitude. And this is very different from 2's complement. So here's how signed magnitude. Let's do 8-bit. So if I want to write a positive number, it's business as usual. Just write down the multiplier for each power of 2. So this is 1 plus 4 is 5. Under signed magnitude representation, I would write -5 exactly the same way, except I'd stick a 1 in the beginning. And this is what we do as humans, right? When we want to write -5, what do? We write the symbol for +5, and we put something different in front of it, right? Well, that's what we're doing in signed magnitude. We're writing the representation for +5, and then we stick this extra thing in front. And this is completely legitimate. We can store numbers like this. We can work with numbers like this. But look what happens if we just try to do +5 plus -5. We would end up with some kind of madness where we say 1 and 1 is 0 with a carry, 1 0 0 is 1, 1 and 1 is 0 with a carry, 1 0 0 is 1. We end up with this, and this looks like, you know, -10. And that's not what you get when you add 5 and -5. You should get 0. So signed magnitude can be used to represent positive, negative integers, and sometimes it is used. But if we want to do arithmetic on numbers represented like this, we have to do some extra work. We need to actually say, okay, this is a -5. Let's use our subtraction circuit, change this to a 0, do our subtraction, write the result in signed magnitude. But if we work in 2's complement, and again, let's do 8-bit. So here's +5. If we take all of these numbers and we complement them, we get this. If we add an extra 1, we get 1 1 1 1 1 0 1 1. That's how we're going to represent -5. And now if we do +5 plus -5, we take the representation of +5. That's the usual representation. We take the 2's complement representation of -5, and we add them together. 1 and 1 is 0 with a carry, 1 0 1 is 0 with a carry, 1 1 0 is 0 with a carry, 1 0 1 is 0 with a carry, and that repeats. And we end up with good old 0, which is what we would like when we take 5 and we add -5. So 2's complement is used often because it lets us continue to do pencil and paper addition without worrying about whether these numbers are positive, negative, or, you know, one of each. All right, other questions? All right, so let me talk about fractions, or decimal numbers, actually. So we know that we can use binary notation to represent positive integers. We know we can use this thing called 2's complement to represent negative integers. Good question. Yeah, so we should probably write a little subscript 2 to indicate this is, you know, base 2, as opposed to, you know, 111 million or whatever. And down here we were adding numbers in binary, and when I got the answer, which happened to be 10 decimal, I wrote a little decimal point there just to make that clear. If we're working on an assignment and it says, you know, using binary, and everything is in binary, we don't need to keep writing the little 2 next to it. But if there's any danger of confusion, right, you can put a radix, like a 2 down here, and you can put a decimal point. But usually it's pretty clear from context. If you're writing this by hand, you can put a little 2 down here. If you're typing this up, you got to do a subscript and all this kind of stuff. But yeah, this one in particular, I put a point there to say that's -10 decimal, not, you know, -2 or something. And the same thing if you're doing hexadecimal, you can put a 16 or an X as a subscript. The book, by the way, has lots of representations for this, especially hexadecimals. So here's the number 16 hex. You'll also see it written as this sometimes. Technically, you could see it like this, base 16. If you're working in a programming language, you could say 0x followed by 10. And this says, hey, the digits that come after this, these are hexadecimal digits. These are multipliers for powers of 16. So you'll see all these different notations. All right, so fractions. If we have a number like 17, and we want to write that in binary, we saw a procedure for doing that. 17 divided by 2 is 8 with a remainder of 1. 8 divided by 2 is 4, 0. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is 0 with a remainder of 1. 0 divided by 2 is 0 with a remainder of 0, and so on. And so in each of these, the quotient became the thing that I worked with on the next line. And then the remainders tell us how to write our number 17, in this case, in binary. So we start from here. This is the most significant digit. So it's going to be 0, 1, 0, 0, 0, 1. And if we continued this step, we would just keep getting zeros over here. So this tells us 17 decimal equals 10001 in binary. And this is 1 plus 16, 2 to the 4th. So that works for positive integers. And if we wanted to write negative 17 in 8-bit 2's complement, toggle each of the bits, add 1. There's our representation for negative 17. So what's missing from here is things that aren't integers. Things like 2.5 or 1.7 or pi or e. But it's the same representation strategy for integers. So when we write a number in binary, this is a multiplier for 2 to the 0, or for the 1's place. The second digit is a multiplier for 2 to the 1, or the 2's place. This is 2 squared, or 4, 2 cubed for 8, 2 to the 4th for 16, and so on. So when I write 10001, I'm really saying it's 1 times 2 to the 0, plus 1 times 2 to the 4th. 2 to the 0 is 1, that's 1 plus 16, that's why that's a 17. But if we continue this on the other side of a decimal point, or what's technically called a radix point, this is the 2 to the minus 1's place. This is 2 to the minus 2, this is 2 to the minus 3, 2 to the minus 4, and so on. These represent negative powers of 2. Well, what's a negative power of 2? This is 1, 2, 4, 8, 16. This is 0.5, 0.25, 0.125, 0.0625, and so on. And so if we want to write the number 2.5, that's going to be a 1 in the 2's place, a 0 in the 1's place, a decimal point, and then a 1 in the 0.5 place. And there's, zeros forever after this, and there's zeros forever in the beginning. And if we wanted to write 1.75, That's a 1 in the ones place, a decimal point. And to get 0.75, we need 0.5 and 0.25, so that'll be 1.11, and then a bunch of zeros. So everybody got the idea of how we're going to represent fractions? We'll talk about how to calculate these next. But does everybody have the idea of how we do these calculations? I'm just going to play with my video until I get some feedback.
Will the second homework have problems for fractions at all?
I don't know. We'll look at the second homework in a little bit. But you can definitely count on seeing this on tests. So if there's questions, it's definitely good to ask. And we're going to go through a procedure for calculating, how to write this methodically. But for now, my question is, does it make sense that this represents that fraction, that decimal number? Makes sense, yes, good. Okay, cool. We'll go with that. I don't know why my display is looking so freaky. I'm just going to run with it for now. All right. So how do we methodically calculate this? We can use the same approach that we used over here, where we repeatedly divided by 2 and we looked at remainders. But instead of dividing by 2, we're going to multiply. So the first thing is we're going to break this into 2 problems. If we want to write the number, 5.2 in binary, we're going to break the problem into 2 separate pieces. First, we're going to figure out how to write 5 in binary, and then we're going to try to figure out how to write 0.2. So this procedure we're going to go through only works for integers that are less than 1. Alright, so how do we write 5 in binary? Well, we've got multiple ways to do that, but we'll find that's just a 101. So the new question is, how do we write 0.2? And so let's convert a decimal into binary. So let's write 0.2 in binary. So I'm going to start off with 0.2, and I'm going to multiply by 2 and get 0.4. I'll take 0.4 times 2 and I'll get 0.8. 0.8 times 2, I'll get 1.6. On my next line, I'm not going to write 1.6. I'm just going to take the thing to the right of the decimal point and say 0.6 times 2 equals 1.2. And on the next line, I'm not going to write 1.2. I'm just going to take the thing to the right of the decimal point and write 0.2 times 2 equals 0.4. 0.4 times 2 is 0.8, and so on. And you've already noticed there's a pattern here. I'm repeating what I'm doing, right? So this pattern of things on the right of the equal signs will continue indefinitely. All right, so how do we turn this into a binary representation? We take the things to the left of the decimal point, and everything over here is going to be either a 0 or a 1. Those are going to give us the bits of our binary representation. So we'll take this digit here, that's a 0, this is a 0, this is a 1, this is a 1, 0, 0, 1, 1, and so on. and we just throw a decimal point at the left. And so 0.2 written in binary will be 0.001100110011 and so on. All right, does this work? So this is the 0.5s, this is the 0.25s, this is 0.125, this is 0.0625, 0.03125, and so on. So right now we're saying we want to take 0.125 and 0.0625 and add those together. That gives us 0.1875. We're getting pretty close to 0.2. And presumably if we add these powers of 2 and these powers and so on, we'll get closer and closer to 0.2. And so if our original question was to write 5.2, it would be 101.001100110011 and so on. And here again, the advantage of writing our numbers in this binary representation is pencil and paper arithmetic still works. If I take this and I add another decimal to it, the number I end up with, if I convert it back to decimal, will be the correct sum. So is there anything maybe a little startling about this fact that 0.2 looks like this? Or that 0.1 looks like this?
I have a question about that.
Okay.
So if we get a binary number that has something similar, but is rounded or something along those lines, how would we translate?
Translate what?
How would we turn it back to its original number? So in this case, 5.2.
Good. So going back is a slightly easier direction. And if we use our little chart up here, let's write this as 1, 0, 1, and this is 0, 0, 1, 1, and so on. Add these powers of 2 together. So 4 plus 1 plus 0.125 plus 0.0625 plus whatever ends up down here, these very negative powers of 2. And if you add all those together, you should end up with exactly 5.2. But here's the thing, there's an infinite number of 1s to the right of the decimal point. We can't just add up these powers of 2 and expect to get expect to get 5.2. Because this is not 5.2. This is an approximation of 5.2. But in fact, to express 5.2 exactly, we need to keep going 0, 0, 1, 1 all the way across. In other words, this is a repeating decimal number. And it's the same situation as when we say 1/3 is 0.33333. Well, if we add, 3/10 plus 3/100 plus 3/1000 plus 3/10,000 and so on, we don't get exactly 1/3 unless we do this forever. And if we stop at some point, if we just take this number, we get something that's slightly less than 1/3 because we haven't added all of this extra stuff over here. And so if we take this number that we've written here we would get 5.1875. It's not quite 5.2 unless we add these other places. And so in binary, if I have a number like 0.1 decimal, 1/10, right? 10 cents if we're doing banking, to represent that exactly, I need an infinite number of binary digits. And if your computer only has 64 binary digits, guess what? The number that I store is actually slightly less than 10 cents. It's actually 9 point something cents. We can't represent a simple number like 0.1 exactly in binary using these notations. And that's a problem if you're using a computer for banking. Because if your computer can't store a number like 10 cents exactly, if it actually stores 9 point something cents, and now you multiply that by 1 trillion, because you're, working with the GDP of a large country, you've got a lot of rounding error, right? And so computers that are used in banking generally don't use this representation for storing numbers. They'll use a different representation that doesn't have this rounding error. And this is one of these things that if you're not aware of, sometimes it can sneak up and bite you. Even if you're just writing a program in a high level language, sometimes you need to know that 0.1 is not actually 0.1. It's usually slightly less. Alright, so one more extension of this, binary coded decimal. This is yet another way that we can store numbers in binary, that we can represent numbers in binary. So suppose I want to represent the number 17. So we can say we're going to do 4-digit BCD, binary coded decimal. And if we're using 4-digit binary coded decimal, how do we write the number 17? Write it as a 4-digit number, and then express each of these digits in binary. So 0 looks like this, 0 looks like this, 1 looks like this, 7 looks like this, and we're done. And this is the number 17 in this representation. And if I wanted to write 5.2, I could write the number 5, a decimal point, and then the number 2. This is super duper easy to write, right? You give me a decimal number, all I have to do is know how to convert the digits between 0 and 9 into binary, and I can just start writing down those digits. And if you give me a number like this, all I've got to do is know what each of these possible bit patterns translates to, and I can write down the digits from the binary. So this is a really easy way to go between decimal and binary representation. And it lets me do something like, if I have the decimal number 0.1, I can write it like this, and it's exact. This is the digit 0, this is the digit 1. So there's no rounding error. But we can't do pencil and paper addition the way that we normally do. These kinds of things don't work. We have to do some extra steps if we want to add two binary numbers that are written using BCD. So it's used if you're worried about rounding errors. It's used if you want to do a lot of calculation between decimal and binary and not so much manipulation. And a lot of machines will do more than one type of representation. They'll let you say, hey, add these two numbers as BCD numbers, add these two numbers as signed magnitude, add them as 2's complement. Alright, so that's a lot of discussion around ways to represent integers. We'll revisit some of that in Engineering 270. It's topical to that. But one of the big takeaways is just this recurring idea that there are multiple ways we can store information in binary or in any system. Most often we use 2's complement with weighted positional notation, but that's not the only way. That's just one that seems to work really well for a lot of situations. But remember that there's always options. Let me grab an attendance here. Alright, let me talk about Lab 1. So Lab 1 is graded. Hold on a sec. All right, so Lab 1 I've graded and handed back to you. And we talked about this on Monday. But any questions about feedback you got on Lab 1 or the grade you got or how it applies to Lab 2?
Professor, I got a quick question.
Yeah.
I remember last class you showed us that you were telling us about a YouTube video you made a while ago about how to like make what's it called?
Circuit on a breadboard? Yeah.
Would you be able to show that link again?
Yeah, so let's see, go down to go to lecture videos. Intro to breadboarding.
Thank you.
Yeah.
What's it like to learn math on
All right. So let me talk about Lab 2. Well, let's wrap up homework 1 first, because we have to talk about analog to digital conversions. But I told you the ADC question won't be the one that I grade. But let's go through that, and then I want to talk about more specific details on Lab 2, specifically what the expectations are for circuit diagrams and such. And then we'll take a look at homework 2. So so homework 1, you should be in good shape with all of these questions except possibly the last one, which was this business of analog to digital conversion. Oh, so question 8, we didn't talk about this, but ASCII is just another way to represent information with binary. And, you know, with ASCII, we're trying to represent characters. So letters or punctuation marks or digits, right? Typically as part of a bunch of text. And so we just have this more or less arbitrary association between characters and patterns of bits. And ASCII is a 7-bit code, and each pattern of 7 bits represents a different symbol. And so you can find in a textbook an ASCII table, or you can find it online. And so A is, you know, the decimal number 65, an uppercase A. B is a 66, C is a 67. The digit 0 is a 48, a space is a 32. So it's just this mapping between characters and bit patterns. And so this is just asking you to write down the ASCII codes in decimal for each of these strings. So this is just getting you to look at the ASCII table if you haven't done that before, and write those down. And so the example up here was, here's some bit patterns, write down the characters corresponding to them. And some of these characters are what we call non-printable. So character 7, for example, is called a bell. And on old teletypewriters, if you printed a character with ASCII code 7, it would actually ring a bell. There's a little mechanical bell and a striker would hit it. And 10 would be a line feed. And it would actually take the paper roll and turn it a little bit so your page moves up one line, and so on and so forth. So go into the ASCII table in the text or find one online and just write down the ASCII codes for these. All right, so the one that we haven't gone over that we need to talk about is analog to digital conversion. So we started off in the beginning of the course looking at this idea that if you have a waveform which is analog, so something that has values that could be positive or negative, we could approximate this by saying, for example, everything above 0 is going to be treated as a logic 1, or a high voltage level, and everything below 0 is going to be treated as a different signal. And so we might do this to approximate this waveform. Does the decimal in question 8 stand for decimal? I'm guessing yes. Let me see. Yeah, decimal. So base 10. So we could approximate this waveform like this, and we could say, this is going to be a logic 1, this is going to be a logic 0. And if we think of this as time, what we can do is we can sample this waveform at different points in time. And we could say this is a 1, 1, 1, 1, 1, 1, 1, 1, and over here it's a bunch of zeros. And over here it's a bunch of ones. And we could code this very complex waveform using just a bunch of zeros and ones. And it's a crude approximation, but good enough for CDs, right? And you could actually take a waveform like this that represents audio. Bye, have a good day. And listen to it, and then you could code it with this single bit, 1 and 0, high and low, and take that coded representation and produce this square waveform and play it back, and it will sound a little bit like the original, right? Now with just a single bit approximation, you get a really, really rough version of your original waveform. But if you use a few bits, we can improve that. So how would we do this analog to digital conversion if we had more than 1 bit available? So let me simplify this a little. Let's think about a signal that ranges between 0 volts and 4 volts. And I don't know what it looks like. Something like this. And if we're going to represent this with a 1-bit signal, what we're going to do is we're going to draw a line right here in the middle. And anything above the line we're going to represent with a 1. Anything below the line we're going to represent with a 0. But we can do better than that. We could say, hey, let's break our input range into 4 buckets. 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And I could draw some horizontal lines. approximately horizontal lines. And basically anything between here and here I'm going to represent with a 2-bit pattern, 0, 0. Anything between here and here I'll represent with a 0, 1. Anything in this range will be a 1, 0, and anything in this range will be a 1, 1. So I'm using 2 bits to represent the value of this waveform. And those 2 bits are telling me, hey, is my waveform somewhere in this bin, this bin, this bin, or this bin? And so everything up to here will be represented by a 0, 0. From here to here would be a 0, 1. From here to here would be a 1, 0. And all of this would be a 0, 1. And this little skinny section would be a 1, 0. And then all of this stuff up here will be a 1, 1, and so on. So if I take that waveform and I try to turn it back into decimal, what does it look like? Well, I might say, you know, 0, 0 is down here. And then at this point it goes up to a 0, 1. And at this point is a 1, 0. And this comes back down to a 0, 1. And this is a 1, 0. And this goes to a 1, 1. And so on. So I get this, you know, kind of square looking approximation. But it kind of follows the shape, you know. It's over here, it rises, it drops again, it rises very quickly, it drops down here, and so on. So this is the idea of digitizing. And in this case, using 2 bits gives us a better picture, right? If we only had 1 bit, and I just cut everything off right here, what would my waveform look like? Well, it would be low, it would be high, it would be low, it would be high, it would be low. All right, so there's 3 concepts related to this, and this is what homework question 9 relates to. So there's the voltage range. Or the scale. And voltage range relates to what's the difference between the lowest voltage and the highest voltage. What's the range of possible values that we want to be able to capture and represent. There's the number of bits. So are we going to code our signal using a single bit, using 2 bits, using 10 bits, and so on. And then there's the resolution. And resolution is a measure of how accurately can we represent a waveform. If I take my waveform and I code it right here as a 1, 0, how close is my understanding of the signal's value to what the signal actually was? And there's a pretty simple relationship between these 3 values. So for example, if I use 2 bits to digitize, right, or convert this waveform into a binary representation, and I say, hey, right here my voltage level was binary 1, 0. Well, if my waveform was anywhere in here, I would store it as a 1, 0. It doesn't matter if it looks like this, or if it went all the way up here, or if it came up and it wiggled around, or if it was perfectly flat. I'm going to code it as a 1, 0. Everything up here I'm going to code as a 1, 1, whether it looks like this or it looks like this. With all this interesting stuff going on, all of that would just get coded as a 1, 1. Because it's between 3 volts and 4 volts. But if I use 10 bits to represent this, well, this voltage would certainly have a different coding from that voltage, or that voltage, or that voltage. And so the more bits, the more closely you can represent the actual signal. So what's the relationship between these? If we have n bits, so given a certain number of bits, 2 raised to that tells you the number of buckets, the number of regions that you can split your signal into. 2 bits we can split into 4 regions. If you have a single bit, you've got 2 regions, high and low. If I had 3 bits, I could break this input range into 8 buckets, or 8 regions. And the deal is, everything within one of these buckets or ranges gets coded the same. So resolution is the ability to differentiate 2 things. And we can only differentiate 2 things if they are in different buckets. If I have a voltage signal right here and I have a voltage signal right here, and everything in this range of voltages gets coded the same, I cannot resolve the difference between this and this. So we get a cool little formula which says the resolution is the voltage range divided by the number of buckets, which is 2 raised to the number of bits. And this is actually so on the solved problem, there's a formula you're given. It's actually your voltage range divided by 2 to the n minus 1. So that minus 1 is there depending on how you're rounding things. And don't get too tripped up on that. But I'm not sure that minus 1 should be there. So if you have 3 bits, we're basically breaking our input range into 8 bins. Which look like that. And so if you know that you've got a signal right here, all you know is it's somewhere between 3 volts and 3.5 volts. And so our resolution is 0.5. Well, that's just 4 over 2 cubed. 2 cubed is 8, it's 4 over 8. Alright, so what are you trying to do on this question 9U? Determine the number of output bits required for each of the following cases. So resolution is voltage range divided by 2 raised to the number of bits. So this is like Ohm's law. If you've got 2 of these, you can figure out the third using this formula. So in part A, we want the resolution to be at least 4 millivolts. And we're told the full scale voltage range is 24, so we know this is 24. We want our resolution to be 0.004. Figure out what the number of bits is. So let's just do part A together. We want the resolution. It says less than or equal to 4 millivolts. If you Determine the number of output bits required. So if we want a resolution of 4 millivolts, that's 0.004. The voltage range is 24, and this is divided by 2 raised to n, where n is the number of bits. And you want to find what the value of n is.
Well, we can't see that.
Thank you.
You still have the page up.
So we want 4 millivolts. The voltage range should be 24, and we don't know how many bits we need. But we know that we have this relationship. So 0.004 is 24 divided by 2 to the n. And we want to solve this for n. So 2 to the n equals 24 over 0.004. I will cheat and use a calculator. So this is 6,000. If we want our resolution to be less than or equal to this, right, then we want 2 to the n to be bigger than or equal to 6,000. And the smallest power of 2 that's bigger than or equal to 6,000 is 8,192. So 2 to the 13th is 8,192. And so 13 is the smallest number of bits we can get away with to get this resolution. Now, if we have more bits, if we have 100 bits, our resolution will be much, much better. It would be 24 divided by 2 to the 100th. It's a tiny little number. But to guarantee a resolution that's at least this good, we need n to be at least big enough to make 2 to the n 6,000 or bigger. So how do you know this is 13? Well, if you know your powers of 2, which you will, by the end of your time at Clark, if you don't already, 2 to the 13th is 8,192. 2 to the 12th is 4,096. That's too small. But if you want to use a calculator, and we don't mind doing some math 111, if 2 to the n is going to be equal to 6,000, n is equal to the log base 2 of 6,000. So you can find a logarithm base 2 of this number. That'll give you a value for n. And so how do you do log base 2? You can do the natural log of 6,000 divided by the natural log of 2. And so 6,000 natural log divided by 2 natural log, and that's 12.55. So you need 12.55 bits to get this resolution, and you can't do a fractional number of bits, so you're going to need at least 13 bits. So that's the methodical way to get that number. All right, so questions about that? All right, let's go back through Lab 2. We went through this pretty quickly at the end of class on Monday. Let me go through it methodically, because there are some very specific details around writing up Lab 2. And I'd like everybody to get 100% on this, because it makes it really easy and fun to grade. So, LED use, we talked about these experiments. It's mainly the last experiment I want to drill into, but let's just review the rest of these quickly. So experiment 1, you're building 3 circuits, each involving an LED, resistor, and these involving an inverter. L is logic 0, so that's ground. H is logic 1, so that's VCC, or 5 volts. And build these 3 circuits, see what happens to the LED, and then try to explain why that's what the LED did. Why does it light up or not light up? Using this idea of what makes an LED light up, having current flow from positive and negative, having a voltage of at least 2.5 volts. Experiment 2, you're building a different circuit with a switch and 2 LEDs. So we can think of this as a circuit that has 1 input and 2 outputs. Build the circuit and make a truth table. And when you write the truth table for the switch, if the switch is open as it's shown here, we write that as a 1. If it's closed so that this end is connected to that, we write it as a 0. The whole trick to this lab is getting your 0s and 1s right. So if you build this circuit and you get everything, you know, wired up and working and so on, and then you just slap down 0s and 1s randomly, right, you kind of miss the whole punchline for the circuit. So when the switch is open, that's a 0. Sorry, when the switch is open, that's a 1. When the switch is closed, that's a 0. It's kind of counterintuitive. When the LED is on, that's a 1. When the LED is off, that's a 0. That one's a little more intuitive. And on is when one side's connected to the other, so there's no resistance. And they're usually, the physical switches are labeled with the word on one side. And if you're not sure in Tinkercad which way is on, use your multimeter. The position that corresponds to 0 resistance from one side to the other, that's the on position. And for us, on or closed is going to be a 0. And this is this switch configuration that we went through on Monday, where you take the input, pull it up to 5 volts through a 1K resistor, and then use the switch to short it to ground. Alright, so build that circuit, see what it does, write up a truth table for it. And then experiments 3 through 5, you're going to build a circuit and write truth tables for those. Each of these circuits has 2 inputs, A, B, and an output. And so you want to go through all possible combinations of the inputs. Make them both 0s, make them 0, 1, 1, 0, and then 1, 1. Again, if the switch is closed, that's a 0. If you're not sure, put a multimeter on the input, see if it's 0 volts or 5 volts. And you should find when the switch is open, this is 5 volts, that's a logic 1. When the switch is closed or connected or on, this is 0 volts, that's a logic 0. Again, there's a typo in the diagram, there should not be a connection between 6 and 7. So you do these 3 experiments, different chips in each case, is a 7408, a 32, and an 04. Alright, and then experiment 6. So this is the one that can tangle you up. So the same intersection, same behavior, same control circuit as in lab 1, but this time we're going to go from the truth table to a schematic. And the schematic should use the integrated circuits that are available in Tinkercad. So if there happens to be a traffic light control chip in Tinkercad, life is good. But there isn't. But there's AND gates and OR gates and inverters and so on. So you can use any of those that are available. So what does a schematic diagram look like? It's got to have logic symbols.
Pages up.
Sorry?
We can't see because the pages up.
Oh, yeah. Thank you, again. So it's got to have logic symbols. And these are our standardized symbols. This is an AND gate. This is an OR gate. This is an inverter. And don't draw pictures of the chips with the pins on the side and connect to the pins, because that doesn't tell somebody looking at it what the logic function is, right? So you want to use these symbols, but we want to know, how are you going to create a circuit with these 2 inputs going into an AND gate and the output of that going into an OR gate, and so on. So we have to add something to our circuit diagram. So the first thing we have to add is components. And so we need to know this is a 74LS08. This is a 74LS32. This is a 74LS04. But if we write those on top of these symbols, our diagram gets horribly cluttered. So up here in the upper right, you have something called a component ID block. And we list the following information. We list the name of each component, and we list the type of each component. So I'm going to need an AND gate. I'm going to call that U1. And usually we call our components the letter U followed by a number. And we start with U1, U2, U3, and so on. So U1 is going to be my AND gate. I'm going to put a U1 right here. And this is going to be a 74LS08. And maybe U2 is going to be my inverter. So I'll put my name U2, and this is 74LS04. And maybe I'll have a U3, which is an OR gate. And that's a 74LS32. So my diagram is pretty uncluttered still, right? And I don't need these U's to understand the logic of this diagram. But to take this diagram and actually build a circuit from it, I need to know, hey, what kind of part am I going to use here? Is it a 74LS08? Is it a 74HC08? Is it a 7408? Is it a 5408? All of these different types of components match this symbol. So the component ID block tells us exactly what part do we use for this gate right here. The next thing we do is we put pin numbers on our diagram. So if you pull up the data sheet for 74LS08, and I think I have one of these handy. Well, let me just grab it from the website. So ENGR250.com, go to component specifications, I'll pull up a 74LS08. And if I look at the picture of the chip, it tells me, hey, I've got 4 AND gates inside here. So if I need an AND gate, I can use any one of these that I want. I'm just going to pick on this first one. And notice one of the inputs is connected to pin 1, another input is connected to pin 2, and the corresponding output comes from pin 3. So I'm going to label these pin 1, pin 2, pin 3. And I'm going to do that here, and I'm going to do that here. And let's say I want the output of this to go into an AND gate with something else. Well, again, I need to specify what physical device is this AND gate going to come from. Well, if this is also going to be a 74LS08, I can use the same one that I had up here. I can say this is also going to come from U1. And what pins will I use? Well, I can't use pins 1, 2, and 3 because I'm using those over here. But I could use this AND gate over here. My inputs come on pins 4 and 5, and my output on 6. So I could do this. And if I had 2 more AND gates, I could still take those from the same chip U1. But if I had a 5th AND gate, I'm going to need another physical chip. So I would add a new component, maybe U4, which is 74LS08, and I would start using U4 for those next AND gates. Alright, everyone good so far? So we've got components with a component ID block, and we've got pin numbers. And you gotta have those on your schematic. And the goal is, once you've got your schematic and we actually build the circuit, which we'll do in a future version of this lab, if your circuit doesn't work, you can use the schematic to debug the circuit, to work through it and figure out what the problem is. And if you were in the lab and you built your circuit and it didn't work, and you went to a lab assistant for help, first thing they're going to say is, let me see your schematic diagram. And if it doesn't have part numbers and pin numbers and a component ID block, they're not going to be able to help you. And if you don't have this information on your schematic and you're trying to debug your circuit, you're working in the dark, right? You're fighting the logic, the wiring, the implementation, the possibility of faulty circuits or a faulty protoboard, and you have no idea which of those you're going after. So this is super important. And it's worth a ton of points on the grading of Lab 2, that you have a good schematic diagram with component IDs, pin numbers, component ID block.
Should we draw it, or can we use like some, I don't know, website that draws it for us?
Either way, but I recommend drawing it by hand. Maybe get a sheet of graph paper or something and you know, sketch it out on pencil and paper first, and then draw a good clean diagram on a piece of paper. But if you want to use software, that's fine. It's almost always going to be quicker to do it by hand, though. And if you happen to have a piece of software that will do all of this for you, I'd say avoid that. Because I want you to get into the data sheets and make sure you understand which pins go to what and so on and so forth. Alright, so there's more in the component ID block, right? Each of these chips that we're going to use needs power connections. This 74LS08 needs two connections. Pin 14 has to go to 5 volts, pin 7 has to go to ground. That's what makes this chip work. It's like a computer. It doesn't do anything unless you plug it in, right? Well, this chip doesn't actually do AND operations unless you power it. So pin 7 has to go to ground, 14 has to go to VCC. And pretty much every chip is going to need that. So we're going to put those connections in this component ID block. And it turns out all of these, pin 7 is ground, pin 14 is VCC. That's not universal though. We'll use some chips where that's not the case. Let's see, would the connection between U2 and U3 be labeled as 2 as well? So U3, I would pull up a data sheet for an OR gate, so 32. And I need two inputs to an OR gate, so I'm going to pick on my first gate. And I can feed into pins 1 and 2, and I come out of pin 3. So maybe I would make this a 1 and this a 2 and come out of pin 3. And so now I know I should have left more space between this and this. Well, if I'm doing this on paper with pencil, you know, I can erase and move this around and so on. And by the time I'm ready to draw with good dark ink on a clean sheet of paper with horizontal lines and so on, I already worked out the details of this, you know, on my scratch paper. Alright, and so an inverter 7404, we've got 6 inverters inside. That's why it's called a hex inverter. And our data sheet tells us somewhere what the action is. You go in on A and you come out on Y. There we go. So the input is A, the output is Y, and there's 6 of these in a package. So here's the 74 LS04 package. And your inverters are set up like this. If you come in on pin 1, you come out on 2. In on 3, out on 4. In on 5, out on 6. In 9, out 8. In 11, out 10. Or in 13 and out 12. And so maybe just to be different, I'm going to use this 6th inverter over here where the input is on pin 13, the output is on pin 12. So I'd label this 13 and I'd label this 12. Alright, well now we're rocking, right? Now if I want to actually build this circuit, it's plug and play. I need a U1, what's that, 74LS08. I grab that out of my parts box or from the sidebar of Tinkercad, I drop it into my proto board. I need a U3, I'll drop that in. I need a U2, I'll drop that in. Now I'm just grabbing a bunch of wires and making connections. I need pin 3 of U1 connected to pin 1 of U3. Pin 12 of U2 goes to pin 2 of U3. Pin 3 of U3 goes to pin 4 of U1. What's happening is while I'm building my circuit physically, while I'm connecting wires together, I'm not thinking about logic. I'm not thinking about binary, 2's complement, product of sums, none of that stuff. I'm just following instructions. This is paint by numbers. Pin 3 of U3, pin 4 of U1, put a wire between them. So a well-written schematic diagram you can hand to somebody who knows nothing about your circuit. In fact, you can hand it to someone who knows almost nothing about ENGR250, and they can build this circuit. And very often, you know, the designer comes up with the circuit, and that diagram gets passed off to somebody who builds it. And then the person who built it, they've got a physical circuit built on a proto board or a circuit board or something. They can take that and this and hand it off to somebody who can test it. And by using this information, somebody can check to see, okay, is there a wire between this pin 3 and this pin 1? Is there a wire between this pin 2 and this pin 12? Is pin 7 of this chip connected to ground? Is pin 14 of this chip connected to VCC? Alright, we add one more piece of information in our component ID block. This is the no connection. And so pin U1, for example, we're using pins 1, 2, 3, 4, 5, 6. Pin 7 goes to ground. We're not using pins 8 through 13, and then pin 14 is connected to power. So no connection would be pins 8 through 13. U2, we're using pins 12 and 13, and that's it, plus the power and ground. So we have no connection on pins 1 through 6. 7's connected to ground. We have no connection on pins 8 through 11. And then pin 12 is right here, 13's there, 14 is VCC. U3, we're using pins 1, 2, 3. We're not using 4 through 6. We use 7, and we don't use 8 through 13. And now we've got even more information to know if we built our circuit correctly. If I look at U3 on the board, I should see wires in every pin except 4, 5, 6, 8, 9, 10, 11, 12, and 13. And if there's a wire missing from pin 3, right, and I look up here and 3's not listed as unconnected, I know I've got a problem. So now I go in here and I look for pin 3 on U3. Oh yeah, it's right there. It should go to pin 4 on U1. Alright, good question in chat. I'll tag it as a topic in the video. Make your schematic before you build the circuit. Right? This is like your flow chart for a program before you start writing code in an editor. This is a blueprint for a piece of furniture before you start sawing wood and drilling holes. This is the description of how you're going to build your circuit. And you gotta have this first. If you build your circuit first, how are you going to get your schematic? You're going to have to reverse engineer it. You're going to have to go through and figure out which wires you had and make this from the circuit. And how are you going to know how to build your circuit, right? So logically, this comes first. All right, next piece of a schematic is your project ID block. This is the fun one. So this usually goes in the bottom right, and this could be you know, a title, Engineering 250, Lab 2, Experiment 4, traffic light controller, and you can put your name, and you can put the date, and whatever else you want in here. But this is kind of like the title page on a lab report, right? This is a little block down here that basically says what is all of this stuff. And you know, if you're designing a computer, you'll get a book with, you know, 500 pages that all look like this, and you just flip through them, right? And so this tells you, you know, what does this page correspond to? This is the least significant byte of the subtraction circuit. And in industry, you know, you typically have something like approved, and there's a place for a signature. Because building the circuit takes time and money, right? Somebody has to actually do that. And so before somebody invests time and money building the circuit, somebody else looks at this and says, hey, this looks good. And they go ahead and they put their signature here. And now if the circuit gets built and it doesn't work correctly, and it turns out the problem was, you know, this wire should have gone over here, well, this is the person you come to and say, hey, you know, you approved this, and this wasn't a correct diagram. You get to approve your own circuits, so you don't need to do that. All right, one more detail. Inputs and outputs. So switches and LEDs. This is Typo City today. So for Experiment 4 and Lab 2, I want you to include switches for the inputs, the car sensors, and LEDs for the outputs, which are the lights. And so, you know, you've got your system diagram that you've done a few times now. And your system diagram looks something like this. Three inputs, west, south, and east, and 6 outputs, which could be green west, red west, green south, green east, red east, whatever you call them, and, you know, indicate what the 0 and the 1s mean here. Well, these, for the circuit that you're going to build eventually, these are going to be switches. So if you want to test your circuit and say, okay, there's a car to the south, you're going to flip this switch to the on position or the off position, depending on how you set this up. And when you look at your LEDs, right, if this output is a 1, this LED, which you'll use a green LED for, should turn on. And all these other green LEDs should be off, and these red LEDs should turn on. And so when we're testing our circuit, and eventually when we're using it, right, we don't want to just take a multimeter and say, is this 5 volts or 0 volts? We want to actually have switches for the inputs and LEDs for the outputs. So for an output, outputs are the easier, right? Make an LED, make a resistor, connect it to ground. This is typically a 1 kilo ohm resistor. And LEDs, we don't need a component ID for them because this is a standard symbol for an LED, but we should label them. So maybe this is, you know, my green east LED. So make sure you label your outputs and inputs. And make sure your labels match your system diagram. Right, if my system diagram says, hey, there's an output called GE for green east, somewhere in my schematic there should be an LED in this case with the same label on it. Okay, try to be as consistent as possible. Right, imagine that, you know, you're in a factory and somebody's going to build 1 million of these units, and, you know, you might label this east or something, or you know, east comma green or something. If it doesn't match this, right, there's an inconsistency. So whatever labels you use for your outputs and your inputs in your system diagram, those should be the column headings in your truth table those should be the LEDs and the switches in your schematic. So all of the stuff should hang together. And then for your inputs, if we want to feed this from a sensor, say, one of these inputs called W for West, remember the way that we hook up switches, take your input, pull it up to 5 volts through a 1K resistor, and then use a switch to allow that input to be pulled down to ground, and then label it the same way as your schematic, as your system diagram and your truth table. So I'll label that West, for example. So I'd probably want to switch here and here and here, or I want them to come from other gate outputs or something like that, and I want LEDs in all my outputs. So for this experiment, when you're done, you should have 3 switches wired up like this. You should have 6 LEDs wired up like this. You should have a bunch of logic symbols and wires connecting them. Each symbol should have a component ID. It should have pin numbers. You need a component ID block and a project ID block. Okay, this takes a long time. I mean, it took a long time just to describe. It takes a long time to write up. But it is totally worth it, because this becomes, kind of the thing that guides you through actually implementing the circuit and testing the circuit. And we're going to be using this circuit for, the entire course. Lab 6, we're going to come back to this, and we're going to add a yellow light. And the yellow light's going to be a variation on the circuit you're coming up with this week. So it's well worth your time to do this very carefully and leave yourself really good documentation. Right? Alright, we don't need pin numbers on LEDs, we don't need pin numbers on switches, because each of those just has an input and an output. And the direction of this tells us which side is the input, which side is the output, and the switch, it doesn't matter. So for switches, we just draw, a little arrow in the air with a connection point below it. LEDs are a triangle with a line. And this is all you should have in your circuit diagram. So don't draw pictures of the chips. It's tempting sometimes to, draw a little picture of a chip like this, and then, come into pins 1 and 2 and come out of pin 3. And that doesn't tell somebody looking at this that this is an AND gate. Unless they know that this is U1 and they come up here and they know it's a 7408 and they know that a 7408 is an AND gate, right? But you shouldn't have to do all of that mapping to know that these 2 lines are being ANDed to generate this output. So that's why we use these standard symbols. Same thing with the switches. Don't draw, a little switch block like this and assume that the person understands what that means. Use this little standard switch symbol, just an arrow hanging in the air, and connects this end to that end. For ground, you can use this symbol, so it's just 3 smaller horizontal bars, one under the other. That's a standard symbol for ground. 5 volts, you can just label positive 5 volts. And I think everything else is stuff you've already been drawing back through 120. So for this experiment, you're only drawing the schematic diagram. You're not building the circuit yet. So lab 3, I think you'll actually implement the circuit in Tinkercad. But for now, the goal is the schematic. But then you'll use this verbatim in lab 3. All right, other questions about that? Yeah, you're welcome. Using the truth table will help. So remember, you've got a truth table, and we're going to talk after the break about going from a truth table to a circuit diagram in general. And so, yeah, the general procedure here is you've got some sort of, design specification. That's like the problem, from the lab. We go from there to a system diagram. and from there we go to a truth table, and from there we go to equations, and from there we go to a schematic, and then we go to a physical circuit. That's basically what we're doing. So the design spec is, build a traffic light controller that, polishes my shoes and controls cars turning left or something like that. We make a system diagram from that. We make a truth table from the specification. After break, we're going to talk about going from a truth table to a set of equations. And then from the equations, the schematic kind of comes out, but then you have to add all of these details. And then from there, you can actually physically build the circuit. And then there's also, testing the circuit. And then we might actually go from, a proto board or breadboard circuit to an actual circuit board with parts soldered onto it. And from there, we deliver it to the customer. So it's kind of a whole development chain. All right, let's do a 5-minute break. We'll come back. I'll take a look at homework 2 with you. And then we'll start talking about how we go from a truth table to an equation, and how we go from an equation to a circuit diagram. So let's take a 5-minute break. We'll come back at 9:36. All right, so see you in a few minutes. All right, we're back. So your homework 1 is due this afternoon. I think it's due at 3 o'clock. And I was hoping to get fairly far through homework 2. And we've only got 15 minutes here. I'm still trying to get used to this 2-day-a-week thing, because normally I teach classes like 5 days a week, and this is trickier. So let me start talking about some of the stuff you need for homework 2, and bring questions to office hours or lab hours tonight or class on Monday. And I may end up pushing homework 2 back a few days if we need to talk about it in class next Wednesday. But for now, let's go ahead and treat homework 2 as it appears on Canvas. So you can click through to it on here, and I'm going to ask you to do questions 1 through 8, and then 10 and 11 U. Don't worry about question 9. And we're not going to get through all of this today. In particular, the stuff with K-maps, we're definitely not going to get through today, but we will get through on Monday. But let me start off with the basics of how to do some of these questions. And this is partially a rehash of ECS 120, and so we've looked at some of this before. The basic goals are managing this map, either between truth tables and equations, or equations and truth tables. So this is kind of the bulk of homework 2. And so if you have an equation and you want to go to a truth table, that's pretty straightforward, right? If you have an equation like, you know, y equals AB bar or BC, you can write a table of your inputs, list all the combinations, and I want to list the value of y for each of these. Well, my suggestion is work methodically. So break this into pieces. Don't just try to go in your head A and B bar or BC and write down y. Let's write a column for not B. And that's easy to do. Just take your B column and flip all your bits. And now I'm going to write a column for A ended with B bar. Well, that's relatively easy to do also. I'm just taking these two columns and ANDing them. Well, when you AND, if any of your terms are a 0, you're going to get a 0. So this will be a 0, 0, 0, 0. And A ANDed with B bar, well, if both of these columns are 1, which is here and here, the AND will also be a 1. If any of them are 0, this will be a 0. And now I'm going to make another column for B ANDed with C. And that's, you know, just the AND of these two columns. So this is 0, 0, 0, 1, 0, 0, 0, 1. And now I'm going to write Y, which is A, B bar, ORed with B, C. Well, now I just have to OR these two columns. And so if any of these two columns is a 1, then the OR will be a 1, otherwise it will be a 0. And so there's my truth table for Y. And the advantage of doing it this way is, number one, you can be lazy, right? You don't have to do a whole lot of work in your head. At most, I'm doing one logic operation, and, or, not, XOR, something like that, on 2 inputs. And my inputs are explicitly written out for me. So, I mean, I can sit back, I can drink a cup of coffee, listen to some music, and just kind of do this without focusing too much on it. Although you should focus on it for homework. The other advantage is when somebody is grading this, they can know, you know, if you got totally the wrong answers over here, Was it complete confusion about everything, or was it one, typo somewhere? And so if I see, all of this looks correct, and this looks correct, but you've got a 0 here, well, that's just a glitch. That's just a typo you made, right? But you obviously know how to do ands, and you know how to do nots, and so on and so forth, and, you lose half a point for that or something. But if all you have is, here's my inputs, here's my outputs, and 3 of these are wrong, it's probably a 0. Because it's like, well, you don't have the correct answer. It seems like you don't understand this. So this is good for partial credit. That's always a good reason. All right, so the other part of this is how do we go from a truth table to an equation? And that's the bigger part of homework too. And that's something we'll probably spend about 2 classes talking on, but let's start with this. So we did this in the beginning of the course, and we know that we've done this in 120 also. One way to write an equation from a truth table is to look at all of the places where your output should be a 1, and write an equation from each of those, and then OR those equations together. This goes back to the combination lock circuit that we built in the beginning. Remember, if we wanted to unlock our cookie jar when the input was 1, 1, 1, if we wanted a 1 here, we said, oh, well, we can just use an AND operation. Let's just take A and B and C. If we're giving our friend a code 101 and we want that to unlock, well, we can express that situation as an AND also. But the AND is we want A to be 1, and we want the complement of B to be 1. We want B to be 0, so B bar would be 1, and we want C to be 1. And this row right here corresponds to the situation where A is 1, and B bar is 1, in other words, B is 0, and C bar is 1, or in other words, C is 0. And this term right here corresponds to A bar is 1, B is 1, C is 1. And since we want Y to be 1, if this is true, or this is true, or this, we can OR these together. And there is an equation for Y in terms of A, B, and C. And that's very methodical. We don't need any insight or intuition. We simply look at each row where the output should be a 1. We write an AND expression corresponding to that row, and then we OR those expressions together. And this is something called a sum of products. It's a sum of products because each of these things is an AND. Well, it looks like multiplication or a product. So in Boolean algebra, the term product refers to the AND operation. And so we have a product, a product, a product, a product, and then we take the sum of those, we add them together, and in Boolean algebra, adding things together or summing corresponds to ORing. So this is an OR of ANDs, but it sounds better to say a sum of products. So this is a sum of products or an SOP representation. And anytime you have a truth table, you can write down a sum of products as long as you know what these terms are that correspond to that row of the truth table. And there's a procedure we can use for writing this for a given row. The way we write down this product term is we just write ABC, same as the inputs. And if our input is a 0, we put a bar on top. If our input is a 1, we don't put a bar on top. And so we can generalize this. And again, we'll stick with just 3 inputs for now. the AND term, or product term, corresponding to this first row is going to be A bar, B bar, C bar. In other words, if A, B, C are all 0, this expression will be 1. And this expression will be 1 if and only if all 3 inputs are 0. How do I know that? Well, I wrote A, B, C, and everywhere that there was a 0, I put a bar on top. So what's the product term for this second row? Well, I'm going to write A, B, C, and everywhere there's a 0, I'm going to put a bar on top. And for this third row, I'm going to write A, B, C, and everywhere there's a 0, I'll put a bar on top. And for the fourth row, guess what I do? I write A, B, C, and where there's a 0, I put a bar on top. And so we can do this for all 8, but we don't need this table if we know the rule. Just write A, B, C. If there's a 0, put a bar on top. And then this last term, we write A, B, C. Well, there's no 0, so there's no bar on top of any of these. And so these are the product terms corresponding to each row of our truth table. And if I'm trying to write the value for an output expression, everywhere that I have a 1, I just write down this product term and I sum them together. I take the OR. Alright, so this is called a sum of products expression. And a sum of products, there's no parentheses, there's no exclusive ORs. It's a bunch of product terms, a bunch of AND expressions, ORed together. And in its most basic form, each AND expression involves 3 inputs, all 3 inputs, and each of those inputs either is expressed in its complemented form or its uncomplemented form. Right? This is very kind of mechanical. This is very easy to teach a computer to do. But it's also the way that we're going to write equations from truth tables for a while. Alright, so that will, you can do question 1, that's writing a truth table from these equations. You can do question 2, which is writing a sum of products for this equation. How do you do that? Well, take this equation, write a truth table, and then from the truth table, write the sum of products. Alright, question 3, we haven't talked about product of sums yet, but you can do the sum of products. So same thing, right? Write a truth table from this, and then write a sum of products. But as you're doing this, think about what it is you're doing, and you'll probably start to understand this at a deeper level. And eventually we'll see shortcuts for going, say, directly from this to a sum of products. But for starting off, work very methodically. Take this, write a truth table for it, and then go through and use this kind of idea to write a sum of products. We'll talk about product of sums on Monday. And we'll talk about min terms on Monday, so leave questions 4 and yeah, you're gonna have to leave most of these for Monday. I'm gonna have to do K-math. I'm just gonna say right now I'm gonna push the homework back a week. So I'm going to change homework to and I'm going to change that to be due a week from Friday. Because we're going to need to talk about this on Monday to get through most of this. So take a start at this, right? Think about some of these other questions. Bring questions on Monday. But Monday we'll go through min terms, max terms, product of sums, and K-maps, and that will give you everything you need for the homework. And then the homework will be due a week from Friday, so that we've got a full week of classes to work on it. All right, so that's the end of our time. I've got lab hours tonight, 5 o'clock to 8 o'clock. If you have questions on the lab or homework or material, definitely come by then. That's a good time to catch me. Office hours Thursday and Friday mornings. If I don't see you there, have a good rest of the week and a great weekend, and I will see you on Monday.
Awesome, thank you so much.
All right, catch you next time.
Thank you.